Thank you, and thank you all for being here today. The Environmental and Social Risk Management team is part of the Environmental Affairs team at Wells Fargo, and we work on sustainability issues both within our organization and with our community partners. So we appreciate all of the support for this event that you all provide. And we are extremely grateful to the leadership of the New Economy, Center for New Economy here at CSU for providing a forum for education and also for inspiring all the conversations that we heard about this morning and the ones that will happen over the next 2 days. With that, I was given the privilege of introducing the first speaker to kick off those conversations. She is a university distinguished professor here at CSU. She is a founding director of the School of Global Environmental Sustainability, a professor in the Department of Biology, and also a senior scientist at the Natural Resource Ecology Laboratory. As a social ecologist and environmental scientist, a lot of her work has been focused in the Antarctic, so much so that the Wall Valley in Antarctica was designated in her honor in 2004. She's highly educated, and she received her PhD from the University of Kentucky in Lexington, Kentucky. So with great pleasure, I introduce to you Diana Wall, Director of the School of Global Environmental Sustainability.
Hi, everyone. We're here for 101. This is going to be an exciting session, particularly because we have two people who are really top leaders in the field of climate science to help us learn what is going on and what are we seeing looking for the future. And I must say that I think that their talks, we're going to have two 15-minute talks and then open the floor to questions. And I think what we're going to find is that they have gone beyond what they do in their everyday jobs to really think and start to work outside our disciplines as broad as they are. First of all, we're going to have Scott Denning, who many of you may know. He's a Montfort professor of atmospheric science. And I should say you can get really good details on them all on page 11 and 12. It's alphabetical order. This is School 101. Look there. And Scott is really well known, not only for his research, for many leadership roles in which he looks at North American climate change or led that for a couple of years or a number of years. He's been editor of journals. He's got numerous papers. He's also the director of education and diversity for CMAP, which is the Center for Multiscale Modeling for Atmospheric Processes. And he's really been working recently to enlarge the understanding of what we know about climate change. So we'll let him have his time. His title for his talk is Simple, Serious, and Solvable.
So I think I have supposed to have control of the slides up here, is that right? I'm pushing buttons and nothing's happening. Well, here we go. Climate change. I got three things to say to you about climate change, and they all start with the letter S, so it's easy to remember. The three S's of climate change are simple, serious, and solvable. We always have to do all three S's. There's a tendency to kind of get stuck on that middle S, sometimes called scary, but I promise you that we will get to the third S, and in fact, that's, of course, the subject of the rest of the symposium as well. So, funny thing that I should say, it's simple. I've been working on this for like 30 years, and if it's so simple, how come we haven't got it all fixed yet? Let me start with some questions. Ever wonder why day is warmer than night? Do you ever wonder why summer is warmer than winter? Ever wonder why Phoenix is warmer than Fargo? You all know why these things are. This is stuff you learned in the 5th grade. Kind of reminding you that really the science that you learned in the 5th grade is exactly what you need to understand climate change. It turns out the answer to all three of these questions is the same answer. It's because of heat, okay? Heat in minus heat out equals change of heat. It's a fundamental property of the universe. If you put more heat into something than you take out of it, it warms up. If you take more heat out of something than you put in, it cools off. Day-to-day weather, that's all about heat coming in and out the sides. A cold front comes in, pushes the warm air out, replaces it with cold air. But when we talk about the climate of the Earth, there aren't any sides because the Earth is round and you can move the heat all around you want on the round ball. It doesn't change the total amount of heat. The only way to change the total amount of heat on the Earth is through the top, by which I mean the top of the atmosphere. All of the heat for the climate system comes from the sun, comes in from the top. But if that was the whole story, that would just be heat in, right? Heat in minus heat out equals change of heat. That's heat in, heat in, heat in, heat in. Eventually the world like burns or boils or evaporates or does some kind of terrible thing. So there's got to be heat going out, again, through the top. It's infrared radiation. You can't see it like you can see the sun, but it's there nonetheless. You put your hand by a burner on the stove, you feel that heat coming off of that burner. That's infrared radiation. That's how the Earth gets rid of its heat, just like the burner from the stove. But to get out, the heat has to pass through the air. And 99% of the molecules in the air are made of just these two gases. The top one is oxygen, the bottom one is nitrogen. They're both diatomic gases, two atoms of the same element glued together by electrons that are shared between them. That's called a chemical bond. Up comes this electromagnetic wave, woo, comes through the atmosphere. And that electromagnetic wave can get a hold of those electrons and get them vibrating back and forth, woo, 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 woo. Don't really make that sound, I make that part up. But the vibrational energy of the molecule has now trapped some of that energy. It's not going out to space anymore. And that energy has been trapped in the vibrations, and the molecule can then de-excite, go back to its ground state, woo, whoa, 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 back to its ground state by sending off a photon of the same energy level as the one that it absorbed. 99% of the molecules in our atmosphere just have these two atoms that they can vibrate in just that one way, because that's the only way you can rearrange the geometry of that molecule. But a tiny fraction of the molecules in our atmosphere have more than two atoms, and by far these are the two most abundant 3-atom or more molecules in our air. The top one's carbon dioxide, the bottom one's water vapor. Now just like O2 and N2, it's only got the two hands, so let's let this be carbon in the middle, oxygen, oxygen. Just like O2 and N2, the carbon dioxide can absorb a photon, go woo, 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 whoa, 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 but there's more. Because unlike O2 and N2, go beep, boom, beep, boom, beep, boom, beep, boom, whip, whip. And each one of these different ways of wiggling that molecule will absorb a slightly different wavelength of infrared energy, a slightly different photon energy level, and that's what makes CO2 a greenhouse gas. It's not because of greed or capitalism or Al Gore. It's just bad luck that the stuff that comes out when we set carbon on fire has 3 atoms and has these different ways of wiggling. H2O is even better because it's bent, but we won't necessarily go into that. On the other hand, you think about what happens if you put lots of extra H2O in the atmosphere. What happens? It rains, but there's no such thing as CO2 rain, so it just accumulates and accumulates in the atmosphere, and that's why this is a bigger concern for us than the accumulation of water vapor. So you've all seen the cartoon, the greenhouse effect. The sun shines down on the ground, some of it bounces back off. The part that doesn't bounce back off warms us up. Then we got to get rid of that stuff. It goes up, it gets caught by these bee-boo molecules up in the sky. Some of that emission of those photons comes back down, warms us up. If you were to walk around with a radiation measurer all over the world all the time, you would find we get twice as much heat down from the warm sky as we get directly from the sun. Twice as much. That's because on the night side there's no sun at all, but the warm sky is always up there raining photons down on us. Good thing, because if it wasn't for that greenhouse effect, the whole world would be so cold that the oceans would freeze to the bottom and we wouldn't be here talking about it. So it brings me to what I call the common sense explanation of the greenhouse effect or of global warming. Many of you are old enough to remember those things in the middle there. Those are called incandescent light bulbs. That's a 4-watt incandescent light bulb. Back when I was a boy, those were Christmas tree lights. When my kids were little, they were night lights helping find the bathroom. If you double the number of these beep-boo molecules up in the sky raining photons down on us, that adds that much extra heat, 4 watts, to every square meter of the Earth. 24 hours a day, 7 days a week, 4 extra watts on every square meter. So look at these tables. Those are about 2 square meters apiece. You can imagine a couple of light bulbs on each table. But it wouldn't just be this ballroom, and it wouldn't just be Colorado. It would be the whole planet 24/7 for the rest of your life and far beyond. If you did that, the climate would get a little bit warmer. Now, maybe not a lot, because just 4-watt light bulbs, but there's a whole bunch of those 4-watt light bulbs, and that would add heat to the climate system. Now, believe it or not, all that was known before light bulbs were invented. The first measurements of this effect were made by this guy, John Tyndall, in 1863. 150 years ago, we knew quantitatively how much infrared energy was absorbed by CO2 gas done in the lab. Since then, it's been done by thousands of labs all over the world. We all get the same answer. There's really no wiggle room around this at all. The CO2 really does absorb heat, and it really does absorb this much heat. Brings me to what I call common myth number one. The myth is the reason people like me are so sure that climate will change when we add CO2 is because it's been getting warmer lately. And it has been getting warmer lately, but we knew this was going to happen before it started getting warmer. We've known this for 150 years, that adding lots of CO2 to the atmosphere would warm the climate system. We aren't extrapolating recent trends into the future. We are applying a basic law of nature. We know it will warm up because we know that when you add heat to things, they change their temperature. This is called the first law of thermodynamics, but honestly, you got to be some sort of egotistical Victorian Brit to call something that simple the first law of thermodynamics. I mean, for goodness sakes, cavemen knew about this. They put the mammoth on the fire and it got hot. But they didn't say first law of thermodynamics. They said, ugh, hot. So we are sure that adding CO2 will warm the climate because we believe in the law of ugh hot. Okay, that's the simple part of climate change. That's how it works. Let's talk about serious. How much warmer are we talking about? Well, it depends. It depends how much coal, oil, and gas we and our descendants choose to burn. That top map shows the amount of warming in this century with low emissions, the bottom with high emissions, but if you look closely at the maps, they're not all the same temperature. Some places get warmer, some places get less warm. The oceans warm up a lot less than the land because the oceans are very deep, 13,000 feet deep. And if you put a 4-watt light bulb on top of 13,000 feet of water, it doesn't change its temperature very much, so you get more on land. The southern hemisphere warms up a lot less than the northern hemisphere because the southern hemisphere is mostly ocean, and the Arctic warms up a whole lot more than any place else because the Arctic is covered with snow and ice, and if you melt the snow and ice, it's dark and it soaks up more sun, and that adds to the warming from the CO2. So if you happen to live on land in the northern hemisphere where it snows, you get extra. You don't just get the global amount of warming, you get about half again as much as the global amount of warming. And if you look at that top map, the middle of North America gets about 3 degrees of warming, and if you look at the bottom map, we get about 6 degrees of warming. But wait, those are Celsius degrees. And if you think about the degrees that we're more used to in daily life, you got to multiply by 1.8 to go from Celsius to Fahrenheit. So it's actually more like 5 degrees of warming for us if we stop burning, and 10 degrees of warming for us if we keep it up. And even that doesn't sound too bad. I don't know, is it like 75 outside today, 10 more degrees be 85. But we're not talking about just today, we're talking about on the average. And to get a handle of average warming, you got to look at a map. This is a map of the average temperatures in the United States in Fahrenheit, and if you're going to warm 10 degrees, you're going to move 2 colors on the map. That means Denver turns into Texas, it means Illinois turns into Mississippi, it means Washington, D.C. turns into Georgia or Florida. That's a lot of warming. We happen to live in a region that's very sensitive to warming because we only have just enough water. There's about 70 million people in the western U.S. that there's not near enough rainfall in the U.S., in the western U.S. to support that many people. The reason why we can support all this economy and population is because of the blue places on the map. Those are called mountains, where the mountains reach up and grab the water as it turns into snowpack. That snowpack then reliably runs down, fills our reservoirs, waters our farms, waters our cities, and so forth. Water in and water out behave just like heat in and heat out. If you warm the air, you evaporate more water. Even if you don't change the rainfall or the snowfall, warmer air leads to more drought because of more evaporation. I'm going to skip this because it's kind of part of the scary thing and move on to solvable. Okay, solvable. It turns out there's 2 ways to solve this problem. One is to use less energy, and the other is to make energy without setting carbon on fire. Let's talk about using less energy. In 2005, I can't point with this thing, that top line up there shows projections of energy use in buildings in the United States, made by the Department of Energy in 2005. You can see that out through 2030, they projected an ever-increasing amount of energy use in buildings. Each line shows another projection made 2 years later, and you can see that in the bottom projection, we project virtually flat use of energy. That's because architects have gotten smart about energy conservation with windows and doors and HVAC and roofs and all that kind of stuff. And it's going to save us $4.5 trillion in the next 20 years just by not wasting energy that we don't need to waste. This shows the price of solar panels since I graduated from high school. The year I graduated high school, was 1977, and in that year, photovoltaic panels cost $200 a watt, or sorry, $77 a watt. They're now costing about 36 cents a watt. The price of solar panels has fallen by a factor of 200 since I graduated high school. The price of solar panels has fallen by a factor of 5 since 2011. It's amazing what this has done. Let's talk about costs to fix this problem. Yes, there's a toilet up here. No, it's not a suggestion. The conversion of the entire world economy to 100% non-carbon energy has been estimated to cost about 1% of the global economy. Now, 1% of global economy is a lot of money. Global GDP is about $75 trillion a year. 1% of that is $750 billion a year. That's a lot of money. That's about what it cost my grandparents' generation to rip up all the streets in London and Paris and every other city and lay sewer lines and knock out water pipes up and down those tenement buildings and put in hot and cold running water and knock out all the internal partitions and put in toilets and sinks and showers. And boy, was that worth it. And it wasn't like that money was gone. Imagine what that money did for plumbers and plumbing suppliers and the grocery store down the street of the plumbers and the children of those plumbers who were able to go to college. And they weren't done yet, my grandparents' generation. They went on, those were my grandparents in the red square up there. They went on to build subways and the electrical power grid and then defeat the Nazis. Each one of those things cost huge amounts of money, and they didn't go broke doing them. My parents' generation built the interstate highway system. They landed on the moon. They fought and won the Cold War. Each of those things was ginormous expenses that didn't make them go broke. My generation invented the PC, built the internet, replaced billions of landline phones with cell phones, and we didn't go broke doing it. My children's generation gets to do it again. They can replace the energy system of the world, and they're not going to go broke doing it. Choose your future. A lot of people think all of our modern quality of life is extracted from the ground. There's value in a lump of coal. You sell that coal to somebody who burns it to make energy. They use the energy to make products and services. You wheel and deal your way to a $75 trillion a year global economy. Maybe that's true, but I hope that it's not really the meaning of history, because if that's true, then when we run out of coal, our descendants go back to the Middle Ages and start to freeze in the dark. I don't want to think that's the way the world works. I prefer to think that we make the world, that it comes from in here, that our most precious resource is between our ears, that we create our well-being through the sweat of our brows and the sparks in our souls. And those are not scarce resources. And before our kids run out of coal, they'll wind up inventing the future. Their future is bright. Thank you.
It's not your typical 101 class, is it? Thank you, Scott. That was great. Now we get to hear from Brian O'Neill, who's from NCAR. He's a senior scientist there. And it's quite interesting that in looking at models, which he does a lot of, one of the things that he's also very interested in is population and climate change. What is the connection between humans and what does it look like for the future? And so many people might call him a futurist person, but in actuality he deals a lot with hardcore data and is a very well-respected scientist. So we're very fortunate to have him here, and he's going to talk about climate change impacts and the reasons for concern. Brian?
Okay, thanks, Diana, and thanks, Scott, for that whirlwind tour of the climate change issue. That was quite an achievement. Now, despite your caution to not get too hung up on the serious part of the three S's, I'm going to spend a little bit more time expanding on the serious part and talk about some ways of understanding what do we actually know about what the consequences of climate change might be for society or for ecosystems. But keeping in mind as well that part of the reason for trying to understand as best we can what those consequences are is to also inform the solvable part, right? If solvable means reducing our emissions and reducing the amount of climate change we get, what do we get for that? What's the benefit? What's the payoff? Well, the payoff is reduced consequences of climate change, that the severity of the impacts on society will be lessened as a consequence. And so we need to understand as best we can not only the energy side of the equation for the solution, but also what the benefit of those solutions is actually going to be. Now, the difficulty in understanding and trying to keep in the brain of a single person some sense of what climate change consequences may be is that there's lots of them and they vary widely. Climate is likely to affect many aspects of society and the natural world, from health to the economy to the coastal storm impacts exacerbated by sea level rise, to agriculture, to the energy system, and so on. And these impacts will be felt differently in different parts of the world. They'll be different in the southern part of the United States from the northern. They'll be different in Europe from the US, or different in Africa. They'll also differ over time. The consequences that we're feeling now, we expect those to change 10 or 20 years from now or 50 years from now. So a lot of times trying to get a sense of, well, what would these consequences be, ends up being a big, long list with many variations, sort of glazes the eyes over, and is tough to have any intuitive sense of how big of a deal is this really. So there have been a number of different attempts to try to develop ways, really they're ways of communicating what these risks are. I'm going to talk about one of those, which is called the reasons for concern. And this is some work that I and a bunch of other people have been involved in updating recently. It's an approach to communicating the risks of climate change that has been around for about 15 years now. This is the third update to them that we've carried out. And what this is, fairly simple. It's taking this long list of different potential climate change impacts and simplifying by putting them into a small number of categories, so that instead of dealing with a 100 or 200 item list, we're dealing with, in this case, 5 categories. And then putting a bunch of people to work, this group of people right here, working with the scientific community to understand from the science that exists today, what can we say now about how high those risks get, how serious they would get with each additional degree of warming, of increase in the global average temperature as we move into the future. And this is often expressed visually as something called a burning embers diagram, which we will look at in just a minute. Okay, so first, what are these categories? So the categories that the reasons for concern ended up with, there's, keep in mind, there's a number of ways to slice and dice this. These are the ones that have been used over the past 15 years or so, are risks to unique and threatened systems. These are ecosystems or combinations of ecological and human society systems in particular parts of the world that are climate dependent and therefore exist in a particular place because of the way climate is in that place. So you think the Arctic, for example, right? There's an Arctic system that depends on sea ice and the typical progression of seasons and seasonal temperatures. Human communities in the Arctic that have particular ways of life that exist as a particular system might be one type of unique system, and there's many examples of that. Risks that are associated with extreme weather events, so any potential consequences related to heat waves, droughts, particularly heavy storms, these kinds of infrequent but severe weather events. Risks associated with the distribution of impacts. This means there may be impacts that actually, if you added them up all around the world, they wouldn't necessarily add up to a large number, but they would happen disproportionately to particular regions or particular groups of people or so on. So famine, for example, current projections of hunger risks from climate change don't add up to large numbers of people globally. But in particular parts of the world, to certain countries, and in particular poor populations within those countries, those risks can be sizable. That would be a distributional risk. Then there are risks that do add up to something substantial globally. So this is the aggregate category. That can be the kind of total dollar damage to the world economy that might result from climate change, or the total number of lives at risk from heat waves, for example, but something that if you add up globally makes a difference. And then finally, risks associated, well, with this, there's a number of things to call them, but one phrase is large-scale singular events. These are big changes to the Earth's climate system that could happen relatively quickly, like the disintegration of ice sheets, although quickly there is a relative term. That doesn't mean overnight all the Greenland ice sheet disappears, but happens at a rate that's fast enough that makes it tough for society to deal with. Large-scale changes to ocean circulation, things like that. Okay, so those are the categories. And here's the Bernie numbers diagram. So this is a representation of what is the current understanding of how serious the risks may be to impacts in these 5 categories based on the current scientific literature. Each of these 5 bars represents one of those categories, right? From 1 to 5, left to right. The vertical dimension here, this axis, is global average temperature. And so the bottom is 0, pre-industrial, before we started emitting anything. The top is 5 degrees, that's 5 degrees Celsius. As Scott said, that's like 9 or 10 degrees Fahrenheit. It's kind of probably the upper end of warming that we might see this century. And that second blue line near the bottom is about the current level of warming, right? We've already experienced something between 0.5 and 1 degree Celsius of warming already. That's where we are now. The colors represent the level of risk, from white, which means no impacts of this kind have been detected yet, so they're not detectable, through moderate to high to very high risk as you go yellow to red to purple. Now, there's sort of specific definitions we used to, decide, well, what does a moderate risk mean, or high risk, or so on. I won't take up time to go through that, but this gives you the general sense, right? And I want to, in a minute, take an example for one of these to say, well, how did we come up with deciding where on this bar should we go from white to yellow? Where does the risk become red or high, and why? What kind of work has been done to support a judgment like that? But before we get into that, you can see some general things, right? That today already we have a moderate level of risk in at least one of these, the risks to unique and threatened systems. We're close to it with 2 of them, the second and third. We're not yet there. We're still in the undetectable risk for the 2 on the right. And we'll come back to why that is for the unique and threatened systems. At the high end, you see once we're around 4 or 5 degrees, risks are high or very high in all categories across the board. In between, and this includes things like the 2-degree target that's a current global goal for climate policy to try to limit warming to, the risks vary. How quickly risks get serious as climate warms differs for different types of impacts. So it happens faster with the bars to the left, a little bit slower for the globally aggregated impacts or the large-scale singular events. Okay, so where do these things come from? So I can't go through all of them, but I want to give you an example for the first one, the unique and threatened systems. So for starters, in this one, the transition from undetected to moderate has already happened in the judgment of this group of scientists. And that is because for a couple of types of unique and threatened systems, in this case coral reefs and Arctic systems, we can already measure the effects of climate change on these systems. And we can say, not only have these been affected, but it's been affected due to human-caused climate change. So we can see things like increased rates of coral bleaching because surface ocean waters in places where coral reefs exist have been getting exceptionally hot, much more so than they have in the past. And so we're seeing these impacts to coral reefs. In the Arctic, we're seeing abnormally low levels of sea ice, the Arctic sea ice. We're seeing changes in the ecology there, species of trees that are moving into the Arctic that weren't there before. We're seeing melting of permafrost, kind of frozen soils that exist there. And we're seeing some impacts on human communities whose lifestyles have to change as the climate is changing there. So this is detectable and happening already. That's the reason for putting that transition there. At the high end, let's skip to the high end here. Why do we have this thing turning purple, very high risk, at about 2.5 to 3 degrees? That is based on risk as determined by studies of potential consequences for species and ecosystems. So again, in the Arctic, projections of the amount of sea ice that would be left in the summer, in the Northern Hemisphere summer, are that by around the time we get to 2.5 or 3 degrees of warming, the summer sea ice, which typically covers all of the Arctic in the Northern Hemisphere summer, would essentially be gone pretty much every summer in most climate model projections of it. So that's a substantial change to the Arctic system with a lot of associated risks. People who study impacts of climate on ecosystems and species extinction, this is a difficult thing to do, project species extinction. So what is normally done is projecting how vulnerable might species be to extinction. One typical way is to estimate, well, if climate changes, how much geographic area will there be available in the future compared to today to support the existence of a particular species that depends on a certain level of rainfall or temperature or seasonal change. And around that level of warming, studies show that very large fractions of several types of groups of species around the world would be at substantially higher risk of extinction due to things like loss of their range. And to illustrate that some of these transitions are more uncertain than others, the transition in the middle between yellow and red, there were some quantitative projections of sea ice and species risks to base that on, but in large part, there wasn't a whole lot to go on, but the idea was, well, if you're yellow now and you're going to be purple at 2.5 or 3 degrees, you got to go through red. And that's going to happen somewhere in the middle, so we assigned that to the middle, but it's a fuzzy location. But that gives you a sense that there is uncertainty in each of these judgments. Some of them are more uncertain than others, and the evidence base is not always as strong for some judgments as it is for others. Okay, so I'm not going to go through the extreme events, but if we skip to just the full picture, each of these little icons represents the primary sector or type of impact that informs the judgments about changes in risk levels, say from white to yellow or yellow to red, for each of these categories. To just give you a sense, point out one other thing, right in the middle, distributional impacts. That judgment is based largely on agricultural impact studies. At what level of global climate change would impacts on crop yields become progressively higher and progressively tougher to deal with, until at the high end, where things turn purple, it gets tough to adapt to those. The impacts are so substantial that we have fewer options for coping with it. Not no options, but fewer options. And that you see that across many of these, the little red scaly thing, which is supposed to be a coral reef, appears in many different categories. The Arctic appears in many different categories. So there's a couple of systems that kind of, as you would expect, if you think about it, are more sensitive for more different reasons than other aspects of ecosystems or society. I mentioned this particular assessment has been done 3 times now. This is what the Bernie numbers looked like in 2001. When this was updated in 2007, it looked similar, but all the red had come down somewhat, so that our understanding of impacts over time has led us to increasing levels of concern rather than going in the other direction. And the current one, again, a little bit of bump down of the red, but we actually added a new color, which led to a lot of jokes, and if next time we're going to use the skull and crossbones or have black or whatever, but this has been the progression over time. So a couple caveats to keep in mind about these judgments, right? The evidence base is uneven. The fact that there's a yellow to red doesn't mean we know for absolute sure when and why and where risks are going to change in the future, but it's the best judgment available at the time. A lot of these are based on projections of physical impacts to the climate system, where what we're ultimately interested in is impacts on people, society, economies, ecosystems, and there's a lot less work that can be easily tied to global average temperature on societies and ecosystems than there is on the climate system itself. And so we have to use this kind of communication tool carefully to communicate accurately what we do know and don't know. So we need more systematic work in order to fill out this picture, right? The goal is, in the end, that we would really have a good map, scientific map to the future about what would the risks be that we would face with 1 degree or 2 degrees or 3 degrees of warming, so we can inform where should we aim, how much warming is too much, and for our solution component, when we, the goal of reducing emissions and therefore climate change, what are we going to get for that? What's the benefit of that investment in terms of reducing these risks? So I will leave it there.
Is it on? Here, try this.
Obviously, thanks very much. And now we'll take some questions. And how do you want to do this, Maury?
I don't have any from the audience,
Okay.
the live stream, but do we have some in here?
Oh, okay. Questions?
Here,
for the
this
audience?
is easy over here.
Thanks for those talks. Very informative. So my question, I'm just going to pose it in very oversimplified terms, but you can complify it. One of the things that seems very problematic to me is the rate at which trees can't migrate as things get warmer. And so if they can't go fast enough to keep up with temperature change, then you might see something like trees dying everywhere. And I can't see how the ecosystem in general operates well without trees, that we start to get all of these compound trace-throughs to all the other species. So could you speak to that problem and where might that occur in terms of the temperature change?
Well, okay, and then I'm going to turn it over because so trees are certainly a problem in terms of how fast they can move. What has to happen, of course, is seeds have to be dispersed, and that takes time. And you got seedlings, and you've got a whole life cycle succession that has to take place. In places like the West, like Colorado, the distances that they have to move are relatively small because we have terrain that you can escape to a cooler climate in say 5 miles or 10 miles if you go uphill, as opposed to much more problematic in a place like central Canada, where you've got hundreds and hundreds of miles to find a climate that's substantially cooler. But it's not just trees. I mean, all natural ecosystems are adapted to certain kinds of temperature, precipitation, and human systems as well. So I think maybe Brian should take it from there.
Yeah, I'm not an ecologist, but part of that group of authors that we worked with on the reasons for concern were, and in order to address that specific issue, like the rate of climate change, and particularly its effect on species and whole ecosystems, a kind of complement to this approach to the reasons for concern was developed, because this one doesn't have the rate in it, right? It just says, well, at 3 degrees, what are the impacts? And as you're saying, they might be a lot different if you get to 3 degrees really quickly, or it takes you a century or 2 to get there. And so there is a version of this reasons for concern burning embers diagram that is based on the rate of temperature change through something that's called climate velocity. And that climate velocity is a lot like what Scott showed in one of his slides, is how fast does the climate conditions that support a particular ecosystem, say in Illinois, move to a different geographic location because of warming. And that's the rate that trees, plants, animals,
Crops?
would have to be able to move in order to, one component of adaptation. So that doesn't tell you which species and where are the issues, but that it is a component of thinking, and that not all communication methods, ways of simplifying things like the burning embers, can really capture all the dimensions of risks.
Okay, I am sorry, but we are going to have to cut this off. We've come to the end of our time, but I hope you learned something, and also that you get a chance to talk to these two gentlemen about their presentations, because I think there's both some new and very informative information to make us think about how climate change is occurring in different places and the impacts and reasons for concern. Thanks very much.
And I wouldn't want to minimize Diana Wall's expertise here. Look at her bio. All of them have quite a bio, but Diana, she always minimizes what she can tell you. So do ask her questions. We're going to take a quick 10-minute break. And if you would take your time and go to the exhibits, that would be great, because they're waiting for you. And we'll take a quick 10 and be right back. Thank you. Please thank them for their great presentation.